Thank you very much for the introduction, and I thank the organizers for this great opportunity to be at this institute and give this talk. This is my first visit also to ICTS. So I've been in Bangalore several times. So thank you. So maybe the optimal is this end. Okay. So as the title suggests, I'm going to talk about certain Hasse principles for rational points on projective homogeneous spaces and a certain class of connected linear algebraic groups over specific class of fields, okay, what we'll describe as so-called semi-global fields. Just to warm up and to begin, let me start with the classical number theoretic situation. A is the number field. So I talked about projective homogeneous spaces. The typical examples are quadrics, and here we have the theorem of Hasse-Minkowski. It simply says that, so suppose omega k is the set of places of k. And for each place of k, let me denote by kv the corresponding completion. Then Hasse-Minkowski theorem asserts that if Q is a quadratic form over K, Q isotropic. Isotropic simply means it represents 0 non-trivially, locally for Kv for all V in the set of places, then Q is isotropic. So if the rank, the dimension of Q is at least 3, these correspond to, and if it's non-degenerate, they correspond to smooth quadrics, which are projective homogeneous spaces under the corresponding orthogonal group or special orthogonal. Okay, so this is one example of a Hasse principle for projective homogeneous spaces. And there is a much more general theorem due to Harder, which in fact states that K is a number, once again the same situation. G is any connected linear algebraic group over K, group defined over K. And X is a projective homogeneous space under G. Then X satisfies Hasse principle for rational points. That is, if xkv is not empty for every V in omega k, then xk is not empty. This is for a general projective homogeneous space. There is a Hasse principle for number of fields. So we'll be looking at more general fields. Just to fix the notation, the terminology projective homogeneous space. By this, I simply mean X is a projective variety which is homogeneous under the action of G. Under an algebraic action of G, such that the geometric stabilizer of a point is a smooth parabolic. I mean, for various characteristics, we need this assumption. It's a smooth parabolic. So this is what I mean by a projective homogeneous space, and this class of spaces can be described as the so-called flag varieties in various Grassmannians. Okay, so this is the variety I'm looking at, and this is the Hasse principle, which is known for all projective homogeneous spaces under any connected linear algebraic group or a number field. Okay. The group is smooth as a group scheme. If yeah, there are some, if Gopal is the expert here. No. That is the whole point. If characteristic is 0, there is no need for the special definition. So everything is okay. Yeah. Okay. This is Harder's theorem is also true for global fields. Yeah, exactly. And just looking at go this way. Maybe you can put it here. No. Thank you. Thank you very much. Okay, so my idea is to go beyond the case of number fields and look at certain function fields, which are function fields of curves or complete discrete valued fields. So the setting I want to move from here is so-called semi-global field. Semi-global field. So for me, a semi-global field is so K is a complete discrete valued field. Discrete valued field. And X over K, you can assume it is a smooth, projective, geometrically integral curve. And F is the function field of the curve. Basically, it's a function field in one variable over a complete discrete valued field. I'll also set up the notation that this little k is a residue field. Okay. And maybe I'll also fix T is a valuation ring. So we would like to discuss Hasse principle for, say, like I started with projective homogeneous spaces, for projective homogeneous spaces over such fields. But here we have to fix what are the local objects, what are the completions we are looking at. So one possibility is you can just look at all discrete valuations of, here there is no, okay, all discrete valuations. And many times it's much more convenient to look at the so-called divisorial discrete valuations, which is a subset of all discrete valuations. I'll quickly say what is the subset of valuations we are looking at. So we have a curve X over K. Yeah, these are much larger. First of all, if you look at all discrete valuations, they may be trivial on K, they could be non-trivial on K. And the divisorial ones, they could also be non-trivial on K, but they come from some kind of geometric situation. Those are but they could be non-trivial on K. Those really contribute, yeah. So this is, so T is the valuation ring, and you take a regular proper model of X is a regular proper model of X. And you take all codimension 1 points here and the associated discrete valuations centered on codimension 1 points. And then there is, of course, no particular regular proper model for a curve, but you look at the collection of all regular proper models, and you take all possible discrete valuations centered on codimension 1 points of all models. Those are the divisorial discrete valuations. So mostly I'll be looking at local global with respect to this because it's more restricted, but this is good enough for us that if there's locally, there is a point globally. You don't have to look at all discrete valuations, but only those divisorial discrete valuations. So I want to mention that if for any of these valuations, if you take kappa as the residue field at V, okay. So I want to describe the residue field in one particular case. Suppose K is one example of such a semi-global field is K is a P-Adic field with the P-Adic valuation. So in this case, if you take function field in one variable and the divisorial discrete valuations, the residue fields, they belong to two categories. One is finite extension of K. It is a P-Adic field. extension of K. These correspond to discrete valuations which are trivial on K. Okay, so they give just finite extensions which are P-Adic fields. And the other ones are function fields in one variable. Function field, it's a global field, I can say. It's a function field in one variable or a finite global field. So these are the two types of residue fields you get over the completions. These are all both of arithmetic type. And the whole point is when you restrict to P-Adic fields, you want to get information about function fields of curves over P-Adic fields, knowing that locally, the local fields are quite nice, that are complete with respect to evaluation for which the residue field is nice, like a P-Adic field or a global field of positive characteristic. Okay, so this is all discrete valuations. The divisorial discrete valuations, which I described there, centered on this. Okay, mostly divisorial. Divisorial. Sorry, it could also be discrete, but it's divisorial. Okay, okay. The residue field, if you take a valuation which is non-trivial on K, it will be non-trivial at P, the prime at the discrete valuation. So it goes down to, so the residue field is the prime P of the T is contained in the valuation ring. So when you go to the residue field, it becomes a function field in one variable or a finite field. So that is those which are non-trivial on K, the residue field is a global field. Global function fields in one variable. This is the arithmetic situation. Okay, so this is the situation. And so the first result of local global principle in this direction is very similar to what I stated as Hasse-Minkowski. This theorem is due to polyethylene. The residue field, I'm saying in the case when K is a P-Adic field. Okay, then this is the description. Just for the P-Adic field. In general, it is also function field in one variable, but over the corresponding residue field. Much bigger, whatever is the residue field. Okay, so the first result in this direction is due to polyethylene, Suresh and myself. So we proved an analog of Hasse-Minkowski theorem. So quadrics over F. F is any semi-global, But we have this assumption will persist throughout the talk. The residue field characteristic of the residue field is not 2. Okay, so quadrics over this satisfy Hasse principle. Hasse principle for quadratic. Quadrics is satisfy Hasse principle for rational points. Okay, a quadric over F, if locally it admits non-trivial 0, if it has a rational point, then it has a rational point globally. This was any semi-global field with the restriction that the residue field characteristic is not 2. Okay, this was the very first general result for such kinds of semi-global fields we obtained analogous to Hasse-Minkowski's theorem. This is just with the divisorial. You can just divisorial discrete valuation. It's enough to restrict to divisorial discrete valuations. So I mean, such kinds of results have quite non-trivial consequences for just, for instance, function fields of, so F is K of X, and K is a function field of a curve. K is a P-Adic field, say. SO. So this is, for instance, the SO. So all projective homogeneous spaces has satisfied Hasse principle. Now, so now if you restrict to K is a P-Adic field, for instance, we observe some nice consequences from this. So when you take a quadratic form over F and look at the completion is a complete discrete valued field with residue field, one of these, because K is a P-Adic field. And these fields are either global fields or local fields. Every 5-dimensional quadratic form has a non-trivial 0 over such fields. Okay, so if you have a complete DVR over the residue field, if every 5-dimensional quadratic form has a non-trivial 0, over the completion, every 9-dimensional quadratic form has a non-trivial 0. It's an easy exercise that over the complete field, every 9-dimensional quadratic form has a non-trivial 0. And if you have a local global principle, you have that over this function fields of P-Adic curves, every quadratic form in at least 9 variables has a non-trivial 0. Okay, this is called so-called U invariant of F is 8, which precisely means that every 9-dimensional quadratic form has a non-trivial zero. This was a big open question until almost the early 90s. It was not known whether this U invariant is finite even, and then slowly things started getting resolved. And myself and Suresh, we first proved that the U invariant is 8 for such function fields and for non-dyadic, but then for all dyadic fields also, Heath, Brown, and Leaf completed the story. Anyway, this is a known fact, but you get it as a consequence from here for non-dyadic P-Adic fields that every 9-dimensional quadratic form admits a non-trivial zero. Yeah, so for the so when you look at completions or the residue field, it is going to be a global field or a P-Adic field, okay, for every such completion. In either case, every 5-dimensional quadratic form with the residue field has a non-trivial zero. Then you can lift it to the information that every 9-dimensional quadratic form or the completion has a non-trivial zero. Okay, because the quadratic form can be split up as some unit form plus pi times unit form. At least one part will have at least dimension 5, and you get a Henselian property that. Okay, so that is the chain of arguments. It's just an example how this kind of results could lead to some arithmetic facts about specific algebraic structures of the fields. This result is also true if the whole field has characteristic too. Yeah, it was already known. Only then the inequi characteristic was the interesting case. If the residue characteristic too also this is true, and the local global, I think it's not yet worked out. So as I'm going to say, there are several results I'll state in some good characteristic case. All of them possibly can be worked out in the difficult characteristic, but simply it has not been done. Okay, so right. So now in the same paper, we made some conjectures very similar to the conjecture for the thing in the number field, Harder's theorem. We conjectured that CTP. After looking at some examples and so on, we conjectured that projective homogeneous spaces under connected linear algebraic groups over we just were careful function fields of P-Adic curves. Function fields of P-Adic curves. We didn't state very general semi-global fields. So we just looked at the function fields of P-Adic curves, satisfy Hasse principle. We just made this conjecture, which is very similar to what happens in the case of any connected linear algebraic group, or function fields of P-Adic characteristic 0. And so we made this conjecture. There's always Hasse principle for all connected all projective homogeneous spaces. Well, I mean, the point of, I'll come back to why we made this assumption made the conjecture only for function fields of only for function fields of P-Adic curves, not for a general semi-global field. So we also made a similar conjecture for principal homogeneous spaces under semi-simple simply connected groups, which corresponds to the usual Hasse principle for number fields, which I didn't mention here. And we also made that conjecture. And this conjecture, okay, both the conjectures have been proved in many cases, but it is not true. The conjecture for principal homogeneous spaces fails if the base field is not a P-Adic field, and it's a general semi-arbitrary field. Okay, so we were cautious, and it was good. But however, I want to only concentrate on projective homogeneous spaces. And so here, what is the standing today for this conjecture? As I said, we had a proof in the case of quadrics, where we didn't really use it as a base field as a P-Adic field, but any semi-global field. And I haven't really thought about characteristic 2, but I feel that it can always be done. Okay. No, we have to assume the quadric is smooth. I mean, that is the point. quadric is always smooth. By definition, yeah. Quadric. Yeah, the quadric is always smooth. Yeah. Okay, so now if you look at this conjecture, what is known in this direction? So there are some progress by a bunch of students of Suresh and so Reddy Suresh. So they proved this conjecture for SL and D, groups of type A and 1. So here the projective homogeneous spaces, they correspond to some kind of generalized Severi-Brauer varieties. And the local global principle here is equivalent to saying that the division algebra index is given by the LCM of the local indices. Okay, this is the kind of result which follows from the proof of this conjecture for SL and D. And some classes of, I'll not go into particular cases, some classes of unitary groups. There are results by some students of Suresh, namely Wu and Guhan, some particular cases. And in fact, myself and Suresh, we completed the proof of this conjecture of whenever G is classical type, all classical type. But once again, I'm suppressing the characteristic, and the residual characteristic is good for the group. Okay. So in the case of orthogonal group, it will be different from 2. So there are specific cases of this conjecture for function fields of P-Adic curves, which have been proved. And if we look through the proofs, starting from the case of quadrics or the proof of Reddy Suresh, it looks that the base field is a P-Adic field is not essentially used in the proofs. Okay. So sometimes some of the proofs work in for more general semi-global fields. So I had a hunch that maybe this conjecture for projective homogeneous spaces could be true for any semi-global field, not just function fields of P-Adic curves, just from the examples and where the result has been worked out to be positive. That seemed to be the case. And in fact, my hunch was not too much wrong. And in fact, we have now a final theorem in this direction. So this, which I want to explain today. So we have the following theorem. This is due to Philippe Gilles and myself. This completely settles this sort of exactly this conjecture much more, that there is always a Hasse principle for projective homogeneous spaces and any reductive group over a semi-global field. I'll just state it. Hasse principle holds for projective homogeneous spaces. Homogeneous spaces under reductive groups over semi-global fields. So no assumption on the base. Of course, there is some good characteristic assumption. Depending on the group. Some characteristics are avoided. So this is the final result, which is proved in collaboration with Philippe Gilles. Whatever I'm going to explain in the rest of the talk is joint work with Gilles on the proof of this theorem. Any questions? Yeah. If characteristic 0, you don't have to assume reductive, like function fields of P-Adic. But this is with respect to avoiding some bad characteristics and unipotence and so on. So we just, if the characteristic 0, we can deduce from this result for all connected linear algebraic groups a Hasse principle. It's a consequence of this for 0 characteristic. Okay. So yeah. So this is the sort of the final result, except there is, of course, this good characteristic assumption, which possibly people can try to overcome. This is not essential, but we do it in this setting. Okay, so the next few minutes, next part of the lecture, I'll be explaining the outline of the proof of this theorem. Okay, so sketch of the proof. So first, we use certain certain techniques from the techniques of patching, which were introduced by Harbater-Hartman-Krashen. I will quickly set this up, Harbater-Hartman-Krashen. So we set up some mechanisms to study homogeneous spaces over this kind of semi-global fields. I will quickly set up this mechanism which I need in the proof. So X over K is a smooth projective curve, K is a complete discrete valued field, and X to T is a regular proper model. And we'll assume that this reduced special fiber is the reduced special fiber. Special fiber is a union of, it's just normal crossing divisor, union of regular curves with normal crossing. With normal crossing. So this is the setting, this is a reduced special fiber. You may assume that would even have loops and so on. So this is the setting. With respect to this, fixing the model and the special fiber and assuming this. So let P be the finite set of closed points on the special fiber, closed points on X naught, okay, which contains all nodal points. This is essential. So when you look at the special fiber, you have these nodal points on the special fiber. We put all the nodal points in this, plus at least 1 point on each component. So when you take out these points, I want the leftover components to be affine. Okay, so you put at least 1 point on each component. 1 point on each component. Okay, so this is some finite set of closed points on the special fiber, and U, this is the components of the irreducible components of this reduced special fiber minus this set of closed points. These are essentially the irreducible components of the special fiber. They are the open components of the special fiber after removing these points. So this is a finite set of closed points. This is a finite set of components, and for each U in U, so we define an overfield FU of F, and for each P in P, we define an overfield FP of F. I mean, I'll not go into the details, it's a bit technical, but FP you can easily understand. FP is, you take a closed point of the special fiber, it gives a it defines its closed point on the two-dimensional scheme. You take the local ring, it is a two-dimensional regular local ring, complete the two-dimensional regular local ring and take the field of fractions. In the equicharacteristic case, it looks like field of fractions of the power series in two variables. It looks somewhat like this in the case of equicharacteristic. So those are the FPs, and you have this FUs. And further, you have the branch fields if P belongs to the closure of the component. For instance, if you take this component U and this point P, so P lies on this component. In this case, you have a branch field FUP. So for each one of these things, and you have this inclusion F, FU, FP, you have a diamond like this for each one of U and P with P in U closure, F of UP. So you have such diamonds whenever P is in the U closure for a pair of P and U. And so you have this inclusion of fields. And one should note that this one is this is a complete discrete completion of FP at a discrete valuation. At certain discrete valuation associated to the special fiber component passing. If you take this special fiber component passing through this point, it defines a discrete valuation at FP, and you complete it. That is precisely FUP, the branch field. So this, you can take it as a black box. You have a bunch of closed points and a bunch of components, fields associated to that, and also this branch fields associated to whenever P is on U closure. In this setting, what Harbater, so we say that G admits factorization, The admits factorization means we are over a semi-global field and we have a model and you have a patch U and P. Okay, all this data is given. G admits factorization if this is the definition. If you take the valued point G of FUP, the branch, these are complete discrete valued fields. You take G of this for all branches P in U bar. Okay, you take all branches and the valued points. This product coincides with product of G of FU, U in U, product of G of FP, P in P. So these fields are FU, FPs are contained in FUP. So you have inclusions of GFUs here and GFPs here. And this product coincides with the product of these two. Then you say that G admits factorization. And they prove a bunch of results concerning factorization and the structure of homogeneous spaces in their very pioneering paper. And and what one main theorem they prove is the following theorem, which is due to HHK. If G is rational, the group, this is a fundamental result they prove, G is rational. What does it mean? G is an algebraic variety. G is a group, it's a variety. Its function field is a rational function field in some number of variables. So if it is a rational group, then G admits factorization. This is a very critical result they prove, factorization. So this is what I want to quote from Harpeter, Hartman, Krashen. Say it again. Yeah. But R trivial is a different notion. Rationality is stronger. If it is rational, it is R trivial. Okay. If it is not known as such, for general G, it will be nice to prove it, but it's not known. Yeah. In fact, I'm coming to R triviality soon in my talk. In the next. The FUP field, the top field I have defined. All pairs UP, P in U bar. Okay, these are also called branch fields. G of the F of branch fields is the product of G of FUs and G of FPs. This is the factorization results, which they prove holds for rational groups. Okay, so how do we use these results? Okay, so do you all hear me? Then I think maybe it is not relevant. So, okay, so our main theorem is that there is a local global principle for projective homogeneous spaces. There are two steps in the proof. We want to adapt this first. Is that, so if, so the standing assumption is that F is semi-global. And F is K of X. And you have a model over T and a patch U comma P, etc. And G is a reductive group defined over F. So let us fix this data. So the first is that, so we talk of some kind of local global principle with respect to patching fields, okay? So if, and X is a projective homogeneous space under G, space under G. So this is the setting. If X of FU is not empty, X of FP is not empty, for all P in P, U in U. So in other words, you can think of some kind of local global with respect to this FUs as U varies and FPs as P varies. This is a bunch of overfields. Suppose a variety here has a points in FUs and FPs for all U's and P's, whether it has a point or F. So that's what we prove. This implies that X of F is not F. So we prove Hasse principle in the setting of patches first. And the second theorem, so Hasse principle for patches implies Hasse principle for this with respect to divisorial discrete. If there is Hasse principle in this case, then we prove that there is Hasse principle with respect to all divisorial discrete valuations. These are the two steps in the proof of the theorem. And maybe I'll just sketch some, so I go on till 10:30, right? 10:20. Okay, so I sketched some ideas in the proof of theorem 1, and theorem 2 will be for another occasion. It's just, I will not be able to say much about theorem 2. So let me just concentrate on what goes into the proof of theorem 1. So first, is steps in the proof of theorem 1. First, as pointed out earlier, we just look at R equivalence classes. R equivalence classes in G. G of some R equivalence classes are in G of L for any or field L of F. So this subgroup of G of L is a normal subgroup of G of L. So these are a set of elements in the group which can be connected to the identity by an open line. Okay, there's a morphism from P1 to G, which is a rational map which connects this identity and this point in its image. Okay, that is a rational equivalence. And RG are those elements which are rationally equivalent to the identity element. This is a normal subgroup of G of L for every field extension of F. So we say that so I want to make it as a definition because RG is not in some sense an algebraic group or something. So it is just defined on valued points subgroup as a normal subgroup. RG admits factorization in the semi-global setting. What does it mean? If this is the definition, product RG of FUP as before is product RG of FU, product RG of FP. This is a definition of these are overfields, and if this happens, you say RG admits factorization. And if you look at, we are looking at reductive groups. If T is a torus, then the first remark, this is polyethylene, which is a consequence of some results with Sansuk on tori. So RT admits factorization, So I'll quickly say why this is true, because this is the first motivating factor for torus, why it admits factorization. So you can take a flask resolution of the torus, which is this is a quasi-trivial torus and a flask torus, and this is an exact sequence. The T admits a flask resolution, and in fact Q is quasi-trivial. It is a rational group. Okay, it is a quasi-trivial torus. This is a rational group. So you have this for any field extension L of F. You have a map from QL to TL induced by T on L points. So the result of polyethylene Sansuk is that eta of Q of L is precisely RT of L. So the R-trivial elements in the torus, L points of the torus, can be captured in the image of this L points of this Q, which is a rational group. Now you see how the proof goes for factorization. Rational groups by HHK, they admit factorization. And anything in the image, you can lift it, factorize, go back. Okay. So this is the critical point, that this flask resolution and this fact of polyethylene Sansuk, that image of QL is precisely the set of R-trivial elements in T. This leads to this factorization for torus. And in fact, the theorem states that we have indeed factorization for any reductive group. It is just the full, it is in that paper that when you take a flash resolution, this image is precisely the R-trivial. Q is the quasi-trivial torus. The quasi-trivial torus is direct sum of a product of things like R L over K of F of GM for finite separable extensions. These are the these are all highly rational groups. So Q is rational, and there's a surjection to T. On L points, the image is precisely the R-trivial. Okay, this is the real, it's a consequence of Koliffelin-Sansuk theorem. Any other question? So our results then state that a similar thing is true for any reductive group. G is any reductive group. RG admits factorization. Factorization if but there is a slight assumption here. We don't prove universally RG admits factorization, which will be lovely, but if provided RG of, you remember these branch fields, I drew a diagram. So this FP to the branch FUP. So this for the points fields to the branch, this is completion of this with respect to a discrete valuation. This is dense in this for the discrete valuation. This is a dense here, but we assume that RG of FP is dense in RG of FUP for every pair U and P. Okay, this is a mild assumption. I mean, this is an assumption we use in order to prove the result that RGFP is dense in RGFUP. Then there is factorization for RG. So this is the result. We prove first factorization for RG with some assumptions with respect. And then the next, I'll come back maybe if I have time, line on this. The next theorem is that, so we pass from, this is the Kneser-Titz groups. So you have this G plus for any extension of G. Let me assume while defining Kneser-Titz groups that these are, G is, it's not necessary for the definitions, but this is what semi-simple, simply connected. In this case, there is this Kneser-Titz groups, which is defined as those generated by, yeah, absolutely, that is the basic thing. Let me assume that G is strictly isotropic. Okay, so in this, isotropicity is an essential condition for existence of unipotent elements. So G plus is the normal subgroup generated by any parabolic and its opposite parabolic. Basically, this consists of unipotent elements. And then these are called so-called Kneser-Titz groups, and there were many questions about the quotients G mod G plus, so-called white-head groups, and so on. I'll not go into this G, but the real connection, and in fact, if you take G of L in this case strictly isotropic, then you can decompose it as G plus of L times P of L for this parabolic. In fact, we can take any, this is independent of P, the parabolic chosen, and G admits a decomposition G plus times the parabolic, points of the parabolic. And the real point why I assumed it is semi-simple, simply connected is that this G plus of L coincides with RG of L. The R equivalence class group coincides with this G plus, in the case G is semi-simple, simply connected, strictly isotropic. So you can think of R equivalence classes as a generalized Kneser-Titz groups if the group is not necessarily isotropic. It's an analog of Kneser-Titz groups. Anyway, this is true. And so naturally, the next statement is that the next theorem, theorem B, is that G plus admits factorization. The Kneser-Titz groups This admits factorization. Okay, so this you can believe it is a consequence of our previous research that RG satisfies factorization, but there is a slight assumption on RG admitting factorization. There's a density assumption, but the density assumption reduces to density for G plus FP and G plus FUP, which is sort of obvious because G plus so unipotent elements. If the field is dense, G plus is dense in G. Okay, so this is certain. This is immediate from theorem A implies theorem B, with some comments. Okay, so once you have this factorization for G plus, I will conclude how the theorem of proof of theorem, the main theorem. Okay, so what we have is all this is because the group is not necessarily rational and you don't have global factorization for group elements. So we are looking at all possible reductive groups. So you have this X is a projective homogeneous space under G. So I think we quickly reduce it to G is semi-simple, simply connected. See, this is very bad notation because the curve is X and the projective homogeneous space is X. Let me call the projective homogeneous space as Y. Suddenly there's a switch in the notation. This is a projective homogeneous space. Okay, so G we can reduce to the situation Y is semi-simple, simply connected. So I'm also going to assume that the patch UP, U is a single U and P is a single point P, and there's only one branch field P on U bar. Okay, so I'll give the proof because it is simpler, but it is not necessary in the proof. You can use Weyl transfer arguments to reduce. In P1, you have a patch like this: one open set, one closed point, and one branch. Okay, so I'll explain this in this situation. So you're given that Y of FU is not empty. Pick a point XU in FU. No, that we don't know it is isotropic yet. But if the statement is true that projective homogeneous spaces locally has a point, it will imply in particular that it is isotropic. But the point is we can't assume it's isotropic to start with. But over FUs and FPs, it's isotropic. Okay, definitely. So okay, so that's the whole point. So you have a point XU, and over FP you have a point XP. Now you take these points over the branch field over FUP because it's homogeneous. There's a transitive action, so there exists GUP, a group element, which translates XP to XU. Okay, because these are two rational points on a projective homogeneous space. So G of UP is in G of FUP, a point over the branch where both these fields sit inside, where you can compare these 2 points. So you have a point GUP here, which translates XP to XU. Okay, so now more or less you can guess the method of proof. So this G. So let me also assume that QU is the stabilizer of XU, which is defined over FU. This is a parabolic. Similarly, QP is the stabilizer of XP, which is over FP. And so let me write GUP is in this group, and G of FUP you can write as G of G plus of FUP, the Kneset's group, times I will take QP. This is a parabolic. QP of FUP. Along the branch or FU or FP, they are all isotropic because there is a stabilizer, which is a parabolic defined there. So you have this equality for semi-simple simply connected, and therefore this GUP you can modify by anything which is stabilizes XP. So you can modify it by anything in QP, and therefore may assume this GUP is in G plus of, because of this equation, you may assume that this is in G plus of FUP. There's no harm because we can knock off this QP because it stabilizes XP, right? And now we have a factorization. So this is theorem B, that G plus admits factorization because G is strictly isotropic over FUP or FP, everything, and there is density, etc. So there is factorization. So you may write GUP as GU inverse times GP, say. GU in G of FU and GP in G of FP. So rewrite here, you get GP XP is GU XU. So you have an element. Where is this element? GP is in the G of FP. This whole element is in X of FP. And this element is in X of FU. For U and P, you have element here and an element here which match literally along the branch fields, which means the so-called intersection property of Harbiter-Hartman-Krashen. This bunch of elements determine an X, which is actually in X of F. So because the intersection of all these FUs and FPs suitably taken is just F. So in a variety, if you have a common point for FUs and FPs for this variety, you already have an F point. So this is what gives that there is a rational point for your projective homogeneous space over the base using the factorization for G plus, which is quite only for projective homogeneous spaces, this kind of arguments work. So I didn't have much time to explain how we prove that R equivalence classes factorize with suitable density. That is a critical point in the proof, but not much time to explain the details. So, and also one major thing which I didn't explain is, okay, we prove everything in the patching setting, and our claim is for all discrete valuations, if there's a rational point locally, for the projective homogeneous space, there is a global rational point. There is a reduction from discrete valuations to patching setting, which is pretty non-trivial part of the proof, okay? And in this setting, there are certain results of Philippe Gilles, in which he appeals to certain kinds of, what are these, they work with this Canadian group on the sort of loop groups and loop algebras and so on. Inputs from there pour into this proof of the fact that over discrete valuations, something is isotropic, it's isotropic over it. It's quite non-trivial business to have this reduction. Okay, but that's also true. Therefore, we have the final theorem for discrete value. I just stop here. Thank you.
Thank you very much for this nice lecture. Are there questions?
Factorization, yeah. No, actually patching, what they do is you have this FUs and FPs, and what they prove is the category of vector spaces or FUs and FPs, first of all. They admit patching, okay, given vector spaces or FUs and FPs, which glue along FUPs, give rise to vector space over F categorically, along with morphisms and so on. Starting from there, they get various kind of patching results for torsors under linear algebraic groups and so on. If you're given a torsor over FU and torsor over FP, and an isomorphism over the branch, you get a torsor over F. Okay, this is the kind of patching setting. Okay, and what is also true is the intersection property, as I mentioned. You take a variety over F, and you have a FU point and FP point for every U and P, and all these points match along the branches. Then it actually defines an F point. That is the so-called intersection property. Okay, so in fact, using just the patching setting, they could prove many things about. They even get this this U invariant 8 for quadratic forms for function fields of P-Adic curves as a consequence of that patching. Of course, residual field characteristic not. Yeah, but this machinery is critical to most of the results which evolved later in this direction. Of course, for discrete valuations, you need much more additional input, but this framework is useful for semi-global fields. Sure, but this is a quite powerful technique. Yeah. And also, this is beautiful how they prove factorization for rational groups. So, but most of our efforts are for non-rational groups like SL and D and so on. We don't have anything given to us factorization, but we have to do some kind of use arithmetic, whatever it is, to prove it can hold factorization without rationality. Okay, but rationality implies factorization, but you don't necessarily need rationality to have factors. It was a big open question for about a decade, or 8 years or so. Do you need really rationality for factorization? Yeah, yeah. Those are all okay. Unirational, sorry, stably rational is okay. Unirational, I'm not sure. Maybe. Stably rational is definitely okay. Yeah, but I am not sure. You have only for stably rational. Generally, it was open, but then we gave an example of a torus, which is not rational, where there is no factorization. Okay, so finally it settled that it's neither necessary nor sufficient, this rational for factorization. Yeah.
Expectation about the Hasse principle for function fields of curves over number fields.
Yeah, that's a big open question. I mean, even for quadratic forms and so on, it will be lovely to have a Hasse principle. Even for totally imaginary, avoid orderings. It will give U invariant as 8, and which is a big open question. We are after it quite a bit, but little bit here and there progress, but it's still a very, very big open question. Things are really, I mean, as I told you in the whole picture, we reduced the patching setting because the base field is a complete discrete valued field, and we use the patching methods. And in the case of number fields, so you have a model over integers, and that's no longer a local, complete local. And so we do not have any given machine to work out things in the setting. And so very interesting questions, but very open questions also in that direction.
Can you say anything about surfaces over the complete discrete valuation field?
Surfaces over complete discrete valued fields, there are some progress by some people, at least for division algebras and indices and so on. Lieblich and a host of his collaborators. There are some results for function fields of surfaces or P-Adic fields, some specific questions like index of algebras, but not in general, no general discussion of Hasse principle. I'm sure there are wide open questions, but since already here we are stuck with problems for curves, so we never went beyond curves.
Other questions? Okay, so thanks.